Okay, yeah. So this is a tricky question, but there's a great idea inside of this question. So let me just summarize what the first part of the question says. Right? We're given charge density that's given by some function. And the little sort of warm-up question it asks us is, what's the divergence of the electric field? And they give us a flashback to equation 685. Well, let's remind ourselves what equation 685 is. Yeah. Let's see, how far back does that go? That goes pretty far back. Gosh, this goes pretty far back.
Thank you.
Yeah, no problem. See you. Okay, here we go. Equation 685. So you remember this is when we were first, talking about how electric fields behave just like gravitational fields, and you all have all these cool facts about, etc. So the question that we're answering now asks us, what's the divergence of the electric field that's created? And here's the answer. It's charge density divided by this little constant, epsilon naught. Okay, now let me go all the way back over to where we were. Okay, so the divergence of that electric field is rho divided by that. Okay, so summary. You give me that charge density, and it'll generate an electric field with that divergence, right? So, wow, that means that the charge density of rho creates an electric divergence, which is not that different. Does that make sense? All right. Okay, so now, fine. Let's take another glance at this equation that we just looked at, this equation here in blue. And we've got an electric field, and its divergence is rho over epsilon naught. All right, so I'll tell you what I'm going to do. I'm going to take this little observation, I'm going to multiply both sides by that same constant. Does that make sense? Let's do that. So this electric field has divergence equal to rho. All right, now what could generate this electric field? Well, here's the thing. Oh gosh, let's see here. Let me use a different color to draw the distinction. It was charge density rho that generated the original electric field, and so this charge density epsilon naught rho would generate, let me not use the arrow, let me use would create that electric field. Does that make sense so far? It's kind of a weird observation, but this distribution of charge density would create this electric field whose divergence is that. Okay. All right. So now, why should theorem 687 be true? Let's find that again. Theorem 687 says every function is the divergence of some vector field. All right. Whoops, too far. All right. Well, suppose that I want to generate this function as the divergence of some electric field. Well, according to this little argument, if you want to generate that as the divergence of something, take whatever that rho is, distribute charges in this way, and that'll create this electric field, and that electric field, its divergence is that. Does that make sense?
I still don't get how it answers the question.
Okay. So here, let me do this a little bit differently. Okay, I'll take a different point of view on this. Let's go back to putting the epsilon naught over here. It's in blue. Gosh. Yeah. Okay. This will be good. So suppose I have some function f, and I want to figure out, what is the electric field, what is the vector field whose divergence gives me f. Keep in mind that's my goal, right? Let's go back to the thing here. My goal is to show that every function is a divergence of some vector field. Okay. All right. So my goal is to figure out, what is this vector field? Someone's giving me some f, and I want to figure out what is this vector field that'll do that. Okay. Well, what I know is that if I take a charge density, that'll create an electric field, and that'll create that divergence. Said differently, whatever your charge density is, the resulting divergence of the electric field is pretty much the same thing, just divided by that constant. Right? So with that observation in mind, how about I pick epsilon naught f? Right? If I pick epsilon naught f as a charge distribution, if I do, like that, right? I make this choice, that will generate an electric field whose divergence is that divided by epsilon naught, in other words, f. So whatever f you give me, I've got a little strategy here for how to distribute electric charges in such a way as to generate an electric field whose divergence is exactly what you wanted it to be. You see the idea there? It's tricky. It's really tricky, right? But there's kind of this sort of feedback phenomenon that, if you look at, let me go way back now to our, where's my mouse? Here it is. Let's go way back to equation 685. Yeah, this equation here. Looking at that equation, the electric field was created by the charge density, but the arrow in some sense goes the other way here, that the charge density pretty much, there's a little constant there, but the charge density is the divergence of the electric field. It's like the charge density is creating the electric field, and the electric field connects back to the charge density by way of divergence. You see what I'm saying? Yeah. So it's not quite fair to say, because of the constant, the little epsilon naught thing, but it's almost like the charge density creates, in the form of its electric field, it creates its own anti-divergence. See what I'm saying? Yeah. It's a really tricky little idea, but it's kind of a neat punchline. Does that make sense?
Yeah.
Okay.